Hello everyone. This video covers first order linear systems, which is part of chapter 9. We're not going to cover all of chapter 9, just on very specific topics. We have throughout the whole class solved differential equations. So now instead of having only one differential equation, you're going to have multiple differential equations, or pretty much a system of differential equations. And specifically, they had to be linear differential equations. In this video, we will only cover homogeneous differential equations. Remember, homogeneous in this case means that B1 is equals to B2 all the way to Bn, and all of n are equals to 0. Right, homogeneous. Okay. Now, we're going to focus specifically on 2 by 2 systems. So the whole video is going to be based on systems that are just 2 by 2. So here you have 2 differential equations, and you have 2 variables, x1 and x2. Now, before we keep going, recall from chapter 8, if you're trying to solve a differential equation of this form, which is also homogeneous, remember you technically have 3 cases. The solution was equals to this, or the solution was equals to this, and finally the solution could be this. Okay, we have done this multiple times. Remember that in the characteristic equation, which the characteristic equation was AR squared plus BR plus C is equals to 0, if it has 2 real solutions, this is what you get. If it is 2 complex solutions, this is what you get. And if you have a repeated solution, this is what you get. This is going to be used in a little bit, so it's not exactly the same thing, but it's going to be very similar. Also, if you remember, the last thing we did was had to find eigenvalues and eigenvectors. If you remember, the process was kind of tedious, especially if it is 3 by 3. But here we're going to focus on only 2 by 2. So if you have a 2 by 2 system, there is a faster way to find the eigenvalues. So this is the formula that we'll be using. Okay. And these two are actually connected. You will see that in a little bit. The thing that we haven't seen before is this. What is the trace? Well, let's say that you have a matrix that looks like this: 3 minus 1 minus 5 minus 1. So this is 2 by 2. So everybody should know how to find the determinant. The determinant of A, remember, is this times this minus this times that, which in this case it will be 8. And you should check that. Remember, this is negative 3 minus 1 times 1 is negative 8. So what is the trace? The trace is the part that is new. And the trace is actually pretty easy. All you have to do is add the diagonals here. Like how much is 3 minus 1? Or 3 minus 1, which is equals to 2. That's it. Now the determinant, remember, was 3 times negative 1 minus 5 minus 1. All right? So we plug it into the formula. So from here we'll get lambda squared minus 2 lambda minus a is equals to 0. and then just factor this. So this method makes finding the eigenvalues a little less messy. You still have to do some work, but it's less messy than before. And from here, the eigenvalues are 4 and -2. You still need to remember the definition to find the eigenvectors. Remember, in by definition, you were supposed to find a minus lambda I, and then you're going to do the determinant of this and set it equals to 0. So you still need to know this for the eigenvectors, and we'll show that in the next page. First, let's look to the case where you have two real eigenvalues. What we do first is rewrite this in matrix form. Okay, so this is the same thing as this, capital X prime. So this represents the vector of x1, x2 prime. So this is equals to 2, 3, 4, 3. So you just write the coefficients from here. X, remember that X means x1, x2. So here the value for A is 2, 3, 4, 3. If we want to use the new formula for the eigenvalues, remember we need to find the trace. The trace of A is just this plus that, which is 5. And the determinant of A is equals to 2 times 3, which is 6, minus 12. And this gives you -6. So therefore, if we use the formula, you have lambda squared minus 5 lambda minus 6 is equals to 0. These factors to lambda minus 6. Lambda plus 1 equals to 0. So the two values for lambda are 6 and -1. Remember that in general, to find the eigenvalues, okay, you do A minus lambda I, and you still need to write this because you're going to need it to find the eigenvectors. If you only need the eigenvalues, you can stop here and you're done. But for this, you're going to need the eigenvectors too. So remember, this will be 2, 3, 4, 3 minus lambda I, which is lambda 0, 0, lambda. And this gives you 2 minus lambda, 3, 4, and 3 minus lambda. And if you want to find the eigenvalue, you will have to find the determinant of this. You don't have to do that anymore because we already have the eigenvalues. But we're still going to need this to find the eigenvectors. For example, let's look to the first eigenvector. Lambda is equals to 6. In this case, if you plug it into this equation, we'll end up with -4, 3, 4, -3. How do we get that? Well, 2 minus 6 is -4, and 3 minus 6 is -3. You want to solve this equals to 0. And you can just focus on one of them because you can see that this can cancel. And this is going to be the case all the time. So from here we'll have -4x1 plus 3x2 equals to 0. Or x1 is equals to 3x2 over 4. Now we're going to use K to denote the eigenvectors. Yes, so eigenvectors. And eigenvectors are not unique. Eigenvalues are, but not eigenvectors. So you can pick whatever you want. So the best number to pick is 4 because the 4 will cancel this one. So if x2 is 4, that means that x1 is going to be 3. If you would have picked this as 1, then this will be 1 and this will be 3/4. All right, let's do the same thing for the second eigenvector, which in this case lambda 2 was equals to -1. If we plug it into this equation again and solve it equals to 0, we'll end up with 3, 3, 4, 4. It will be 0, 0. So from here, we have 3x1 plus 3x2 is equals to 0, which means x1 is equals to minus x2. You can also use the bottom if you want. It will give you a different eigenvector, but remember the eigenvectors are not unique. So therefore from here, we can say that k2 will be equals to 1, negative 1, or you can pick minus 1, so this will be 1. So either one is fine. So therefore the solution is going to be C1. So this is just a constant. That's not a vector, a constant. And then the first vector was 3, 4. So this is K1. And it will be e to the 6t plus the second constant, the second eigenvector, e to the minus t. And that's the answer. Notice the similarity from what we did before. If before you got, let's say, R1 equals to 6 and R2 is equals to minus 1, then the solution will be C1 e to the 6t plus C2 e to the minus t. So you can see the similarity between the two methods. All right, you didn't get the last example. Here's the chance to redeem your sins. Let's try one more. So this is the system of equations we have. Remember, the first thing you need to identify here is what's the value for a. So here a is going to be 3 minus 2, 2 minus 2. And let's say that this one has an initial condition 2. Let's call the initial condition x0 is equals to 1, negative 1. So that will be the initial condition. So first thing, what is the trace of A? And remember, the trace is this plus that, just the sum of the diagonals. So in this case, it will be 1. And what about the determinant of A? The determinant is minus 6 plus 4, which is equals to minus 2. Hence, the equation for the eigenvalues will be lambda squared minus lambda minus 2 is equals to 0. If we factor this, we get the following two eigenvalues. Lambda 1 is equals to negative 1, and lambda 2 is equals to 2. It actually doesn't matter which one goes first, you just have to keep track of them. Also remember, for the eigenvectors, you need to write this out. So a minus lambda I is equals to 3 minus lambda 2 minus 2 and minus 2 minus lambda. You should stop the video and check that this is correct. All right, so now let's find the eigenvectors. So let's look to the first eigenvalue, which lambda 1 was equals to negative 1. So if we plug in negative 1 in here, this is what we get. 4, negative 2, 2, and negative 1. Why? Because this is minus 2 minus 1, so that's plus 1. And remember, we're trying to solve this equals to 0, which is actually called the null space. You only focus on one of them. Doesn't matter which one. So let's say you look to the top. So we're going to have 2x1 minus x2 is equals to 0. So this means 2x1 is equals to x2, or x1 is equals to x2 over 2. So therefore, the first eigenvector, if you pick x2 to be 2, then this will be 1. Again, remember, the eigenvectors are not unique, so you can pick technically whatever you want, but this is probably the easiest one. All right, let's do the same thing for lambda is equals to 2. So in this case, this one becomes 1 minus 2 minus 4, 2. And remember, you're trying to solve this equals to 0. From here, we get now that x1 minus 2x2 is equals to 0, or x1 is equals to 2x2. So therefore, the second eigenvalue will be 1, 2. If x2 is 1, so 2 times 1 is 2. So therefore, the solution x will be equals to c1, the first eigenvalue, e to the minus t, plus c2, second eigenvector, e to the 2t. Now, if you have initial conditions, you just have to do a bit more of basic algebra, and it can be a little tedious, but all you have to do is plug in the values. So remember the initial conditions. We have the initial conditions was the x of 0, the x of 0 was equals to 1, negative 1. Which, if you plug in initial conditions, it will give you this. This is equivalent to having c1 plus 2c2, and then 2c1 plus c2 equals to 1, 1. And once you solve this, you'll find out that c1 is equals to negative 1, and c2 is equals to 1. Hence, the final answer will be x is equals to minus e to the minus t plus 2e to the 2t minus 2 equals to the minus t plus 2, sorry, just e to the 2t. Right, this should be e to the 2t. All right, so now let's look to the complex case when you have complex eigenvalues. And by complex eigenvalues, it means this. Lambda is going to have a real part, which is going to be r, and an imaginary part, which we're going to call it mu. Okay? And the eigenvector is also going to have a real part and an imaginary part. So k is going to be a plus bi. So this is the real part. This is imaginary, and these two are vectors. So a and b are vectors. Here, r and mu are just scalars or just constants. So make sure you are aware of that. So this is a vector, this is a vector, and these are scalars. So once you figure this out, then the general solution is actually very simple. It's this. It's pretty long, but it's always the same answer. So once you figure r in mu, r goes here, mu will go in here, and then a and b, remember, are vectors. And the process is very similar, except that now the eigenvalues will be complex. For example, let's say you have this system. So here, x prime is going to be equals to 2 minus 5, 1 negative 2, x. Here, a is equals to 2 negative 5, 1 negative 2. So the trace of a is equals to 0, in this case. And the determinant of a is equals to 1. Okay? Or negative 4 plus 5 is 1. So therefore, to find the eigenvalues, we will have lambda squared minus 0 lambda plus 1 is equals to 0. That means lambda squared is equals to -1, or lambda is equals to 0 plus or minus I. So that implies that R is equals to 0 and mu is equals to 1. Here you have technically two eigenvectors. Lambda 1 is equals to I, and lambda 2 is equals to minus I. And you can use either one to find the eigenvectors, and you only need one of them that you will see right now. Remember that before you find the eigenvectors, you need to go back to this A minus lambda I, which in our case, this will be 2 minus lambda minus 5, 1, and then minus 2 minus lambda. Okay. And if you plug in lambda is equals to I, we get the following. You end with 2 minus I, 1 minus 5 minus 2 minus I, and remember you want to solve this equals to 0. Again, you can pick either this row or the next one, it doesn't matter, because remember the eigenvectors are not unique. So from here we get 2, from the top, you get 2 minus I times x1 minus 5x squared is equals to 0. If you solve for x1, you end up that x1 is equals to 5x2 divided by 2 minus I. Remember that I is the square root of -1. So therefore from here, the first eigenvector, which is actually going to be both of them at the same time, is going to be 5, 2 minus I. So now you break it into the real part and the imaginary part. So this will be 5, 2 plus 0 minus 1 I. This is the vector A, and this is the vector B. So then the next thing you do is just plug it into the equation, to this one. So we plug it in there, we get the following. X is equals to C1 e to the 0t, because remember R was equals to 0. The first eigenvector was phi 2, and then this is cosine t, minus 0 minus 1 sine t, plus c2 e to the 0t, phi 2 sine t, plus 0 negative 1 cosine t. Again, all we did was just to follow this formula right here, this one. Okay, just plug it in. Okay, if you simplify, we end up with the following. X is equals to C1 phi cosine t 2 cosine t plus sine t plus C2 phi sine t 2 sine t minus cosine t. And that's it. Now you have initial conditions. You can plug it in here to figure out the value for C1 and C2. Otherwise, this is it. Also, notice here how we only actually find one eigenvector, and the eigenvector has the two parts you need, the real part and the imaginary part. So you don't have to find two separate eigenvectors. We only use lambda 1 equals to I. We could use lambda 2 is equals to minus I, and it will give you different eigenvectors, but the answer will be the same at the end. So if you could use this, then this part will be like minus 2 plus I. This will be 2 plus I, and you will end up with different eigenvectors, but the solution will still be considered correct. So again, when it comes to complex eigenvectors, eigenvalues, you only use one, and you will get the two parts that you need to get the answer, and that's it. Now this is the last thing that will be on the exam number 2.